Hello everyone, this is Hacken. In this video today, I'm going to talk about Mobius strip modeling in Grasshopper. Most of you may probably have known the Mobius strip by its mathematical definition. But in Grasshopper, the concept of Mobius has extended. You can say any base geometry that flows along a circle to meet its own end is a Mobius strip. And this gives us unlimited imagination. Just like what we did last time for the vase, let's first take a look at a real model I printed myself to create our own logic structure before we starting on Grasshopper. As I said, Grasshopper logic is what is called value that makes everything happen. As you see here, we can tell step 1 is to create a base geometry and a track to flow along. The track is of course a circle, and the base geometry here is actually a triangle. I just filled it, and you probably already know how to do that. We will go about it later. And step 2 is of course to flow the triangle onto the track. And step 3, as you see, is rotation. Keep the 3 steps in mind. And after we have done all of these, you probably may think we are happy. You probably think that rotation will be the last step. But actually, I can tell you in this model, in this case, it's not as simple as you think. Not like the vase. Because the vase at the top has a bottom, and they are not, the two ends are not connected to each other. This is a ring. So I will go further from the rotation when we get there. And right now, let's go to Grasshopper and work on the first logic structure we have just created. As I said, the first step is to create a base geometry and a track. The base geometry is a triangle. Give it a number 3. And yeah, here's the we also need the radius. And step 2, or not step 2, the sub-step in step 1 is to create a circle. So now we need to flow the base geometry onto the track, onto the circle. You probably are already familiar with this icon, this tool. Let's see, input the curve, and n again is a number of reference planes. Let's do 40 again. 40 is a good number. And to flow this onto the circle, we just input the planes we have to the base geometry. Here we go. Now, yeah, before we go to the third step, let's take a look. See, there's no edge in this model, so we just go fit it. Put 5, get it 5. Give it a radius. I don't know if it's big enough, but yeah, let's try. Okay. Make it more clear. Good. Here we go. We have already created a set of base geometries, and the third step is to rotate. Let's see. We go to rotation first. Input the geometries we have, and rotation planes, we already have it. And as for the angles, we make a sequence. Another sequence. Since this is triangle, let's go to pi first. Not sequence. Let's do domain. It's easier. It's a triangle, so what we do is to divide 2 pi by 3. And we have the domain. In order to get 40 values as the output, we divide the domain by 39. The same strategy we did before. Okay, let me explain one more time. You have a domain. You have 40 points, 40 values as the output, which means you have 40 points along the domain. So you divide it into 39 parts. That is what we do in mathematics. Input to angles, and let's see. Yeah, it's already working. Good. Now we have all the base geometries rotating in place. Let's go Loft. Okay. And you already noticed that there is a gap here. Right click on the icon, go to Loft options, close Loft. Here we go. We wanted the two ends to connect to make a continuous surface, but it's the sharp twist here. Do you know what the problem is? So this is what I say. It's kind of tricky here. The reason is that the starting geometry here is in its original place. We can see from the list here, the sequence. Let's go panel check. The first item is rotated by 0 degrees. Okay. And the last one is divided by, actually, this is 2 pi over 3. So, it does not work. This is what usually happens in Grasshopper. You have created your own logic, and when you go for practice, you found it's not working. Problems do happen, and to correct all the errors, we need to go back and check our logic structure. Probably we need to do it in another way. So let's see what's one of the right methods to make this happen. Sorry, here's another problem, I believe. Oh, that is why. I made a mistake here. I should do minus. Instead I did division. But yeah. Let's do the same thing. You can see. Right? Oh. Let's check it one more time. Okay. So what we can do now, the key to create the continuous Mobius strip is with the ends, the gap here. One way to do it is to cut the circle, to cut the strip in half. Say, just imagine I have a line here. We go to Loft, the left part first, and we go to Loft, the right part second, and we combine the two surfaces. Does it work? We'll go check it. To do that, we need to pick specific items from the original set. So let's go sets and sublist. So we have 40 items here. If I pick 20 items from 0 to number 19, let's see what will happen. Okay, let's check it again. Input number 1 base list, yes. Input number 2, domain of domain. Okay, let's go to domain. We starting number at 0, and the ending number, as we said, it should be 19. How do we get it? Try to work all of this on the logic map instead of just directly typing 19 as input, because when we change the potential geometry parameters here, if you do number 19, it doesn't work. So we divide the number of reference planes by 2. We have 20, and divided by 1. Sorry, minus 1. Let's see. We have 19. Okay. We have 20 items. No. So for the second half, of course, we go from 20. Here's 20. No. Here we go. Starting from number 20. Interesting. Ending at number 39. Here we go. "20 locally defined values." Yes. Let's check. So for the first half, we have 20 items, starting from number 0 to number 19. And we go loft it. Let's see what happens. For the second half, loft as well. So here we have 2 gaps. So for this one, you cannot really end for the first half. You cannot really end at number 20. We need one more base geometry here, so you can connect to the second half. And for the second half, we need one more geometry here to connect to the first half. So let's correct the error. Go this way. Okay. So we're happy with the first half here, but for this one, if we because it has only 40 items, the potential 41 number 41 is actually number 0, the first item in the original list. But if we add the first geometry directly to the second half we already have and loft all of them, what we have, the result should be the same as we did for the first time, which is not working. So now what we need to do is pick up the specific item from the original set. And the default value is number 0. It should be, yeah, it's right, because you can see the green here. To make them match, let's we need to rotate the new item as well by the degrees we have got here. So we need to rotate it. Let's go rotation. Here we go. And for the rotation plane, we still need to pick the item from the planes. Input to the rotation plane and a rotation angle. We already have it here. Okay, so let's we have two sets here. The first set is the second half of the original set, and the second set is a single item, but it's still the same. We'll go to merge. Let's see what happens. Okay, see. So when we see this stuff, we go loft, but it doesn't work. Here's the problem. You will always know this when you go familiar with Grasshopper. But now that I can tell you, it is as a tip. The reason why I always use panel to check all the data I have got is that I want to make sure all the data types match with each other. So let's go what's wrong with it. This is the second level data. This is at the third level. The data type doesn't match, so they do not actually work together. The way to do it is go flatten, flatten. Let's see. Okay, the first level data. The flatten tool is to bring all the levels down, no matter at what level the data is. It will always convert it into the first level data. It's a long talk for the data type. We'll probably go there in the future, but now let's solve the problem at hand first. So here we go, and we have two already get two serve, yeah, which matches with each other very. It's good. Okay, we go to surface, put them together by grep join. Here we go. So we have already created a Mobius ring. Let's go check the picture. It's twisted more sharply than the model we have here. The way, because it lies here. If we do math multiplication, type in the number, you want to twist it, input to domain, input to angle. Let's see, this is original position. 1, 2, 3, 4, 5, 6, 7. Here we go. This is what you get. So okay. For the scaling part, if you want to really scale it, as you see in the picture, this part is quite big and this part is quite small. Yeah, just take the same strategy as we did for the vase. It's not a big problem. So here I want to address a question. Some of you may probably have the same question already. What if I do not really want to do a triangle? I would like to work with a square. If I will do square now, see the end doesn't match, or we're going to go to pentagon or hexagon, and so on. How do I make sure? How do I make the number of sides, the base geometry, also another parameter? And we will talk about this next time. And yeah, today we just stop here, and thanks for watching.